different speakers for you tonight. The first is Dr. Dursun Delen, who teaches here at Oklahoma State University. He's going to kick things off for us. Is there anything else we need before we get you started?
No, not really.
Okay, cool. Well, we'll go ahead with it. Please post your questions as we go. Otherwise, thank you, Dr. Delen.
Thank you, Scott. Hi, everyone. Thank you for attending in person. And for those of you who are online, thank you for being a part of this event, Data Connect event. So I'm not going to spend a lot of time, but I want to share my experiences in tuition with respect to KNIME and how KNIME is changing educational world, especially for data science and business analytics. I've been in the world of analytics in general. Some of you already know because some of you are my graduate students, over 35 years. So my professional experience with processing data for smarter decision-making dates all the way back to mid to late 1980s. Mainframe computers, COBOL programming language, smart pricing systems on, hardly relational databases. For the last 20 years, so about 15 years of my experiences in industry before I joined academia as a faculty about 21 years ago, and my analytics experience in education is kind of based on last 21 years. So I have seen the progression of computers, analytics, using data, using models, using evidence-based intuition to make better decisions. Let me see. Okay, awesome. So analytics and data science, right? Depending upon which department, which angle you're looking at it, you might call it one way or the other. In business school, we tend to call it business analytics because there's a business keyword in front of it. If you go to engineering or computer science or statistics, quite likely they might actually call degree programs under the label of data science. But regardless of where you go, it's a hot topic. It's probably hottest topic in the business world and in academia, largely because of the following factors. So these are the top factors that I can come up with. First and foremost, we need to make smarter, better decisions. We need to make optimal decisions to get the most out of our limited resources. Number two, we have plenty of digitized data. Data that we did not have never had the opportunity to actually deal with that level of data, not even imagine how big the data might have been. We have advanced hardware and software, and they're advancing in an exponential speed. The latest trends in ChatGPT, deep learning, there is no ceiling as to where we're going to slow down. If anything, we're going to reinvent the algorithms to make them faster, smarter, better in AI and data science analytics as we go along. And there's also this changing culture in organizations that companies' managers are more likely to look at data, crunch numbers, and make decisions, as opposed to relying on their intuitions, gut feelings, and sixth sense, whatever you actually call it. So all of those combined are making analytics, data science, hugely popular in industry, and that is the demand that's fueling a whole bunch of academic programs in academia. We want to meet the demand of industry, and we're kind of falling behind, trying to catch up, trying to create this linkage so that we would train you, educate you on the things that they actually need as far as analytics and data science is concerned. So why is it difficult to teach analytics compared to some of the other more traditional disciplines, courses, and classes? First and foremost, the scope is broad and it has not been settled yet, meaning that what constitutes analytics data science is different depending upon who you ask. What is included, what is not included, where are the boundaries, what is more important? Some might be more machine learning oriented. If you go to an engineering, it might be more simulation optimization focused. So depending upon who you talk to, right, there is no standardized definition and scope of analytics. So because of that, it's hard to decide what to teach, what to leave out. Okay? Number two, it's an interdisciplinary field, right? It's not belong to, say, engineering or stat or computer science or business school or MIS or IS. It's all of that. And because of that, right, how do you craft a curriculum that can take advantage of this multidisciplinary approach to analytics? You want to teach your students both hard skills, programming, modeling, analysis, but at the same time, the soft skills, project management, identifying business problems, managing teams to get the best out of them. And analytics is still experimental. We call it data science because we would like it to be a science. It's far from it. It's more of an art than it is science because you need to try different options. It's more experimental, try and error still because it has not been settled. So it's a moving target that we're trying to hit every step of the way. And when you're teaching and when you're actually conveying that message, the trade-off is between syntax and semantics. Are you going to teach your students syntactic details of programming, or are you going to teach your students concepts, best practices, foundational constructs that actually makes data science analytics happen? Especially in business schools where the technical skills might be somewhat limited or not really audience might be interested in it. How do you teach analytics at a level that they actually graduate and be productive wherever they go soon after they actually graduate? So what kind of tools that we actually use in analytics? So I come up with this binary classifications when I talk about tools in analytics and data science. There are tools that are free, right? You don't have to pay for it, like KNIME, like Python, like R, and there are tools that you have to pay for it. Maybe you don't because you're a student, if you're a student, right? Maybe your school might actually pay for it, or your professor might actually get into an agreement with the company to acquire student version of those commercial tools that you can actually use. The second is the open source versus proprietary. So there's an IP embedded into it. So it's a black box. It does what it does. You don't know how it does what it does. In open source, you can go all the way down to the algorithmic details and then not only see how it does what it does, but also change it if you want it, if you know how to change it, if you want to change it. There are analytics tools that can install on your computer. Some might not install on some of the operating system, but we're kind of overcoming with that limitation with the virtual servers, virtual machines, and so forth. And some of them have the server-based implementation, so cloud-based, server-based. Quite a few tools actually have, one foot into local and the other foot in the server, so you can actually develop on the local and deploy on the server. And then some tools are going to be programming, syntactic, like Python and R. Some tools like IBM SPSS Modeler, SAS Enterprise Miner, KNIME, Orange, Wacom, some of them are going to be visual. So you're going to build the pipeline, right? The functions connected to each other in a visual sense, right? We call those low-code, no-code tools or no-code programming, especially when your audience is not programming savvy, right? Using those visually oriented programs that also embraces programming if and when needed, you get a lot better results. So there are a whole bunch of tools out there, falls into some of these categories. The tool that we're focusing on today, tool that I've been using for 8 years now, I discovered it about 9 years ago. Before then, I was using other proprietary commercial, again, partially visual tools. And then shortly after I discovered KNIME has become my primary analytics data science tool. I use others on a as needed basis. I do program in R for some pretty visualization, some special functions. I do Python every now and then if I need to, but bulk of everything that I do, teaching, I do on learning myself, new algorithms, new application areas, and doing work, maybe consultancy or kind of mentorship to companies and nonprofits. I use KNIME. for a very valid reason that I'm going to talk to you about. And early in the analytics continuum, we call this people who does data science analytics as data scientists. And there were very few of them because we loaded a lot of qualities, skills into that single label. We wanted those people to know programming, scraping, hacking, all the very low level coding, as well as the managerial, project management, human skills, communication skills. And it turns out there were very few of them to go around. And then shortly after, we figured out that maybe data scientist is not a person, it's a team, right? And then this data scientist title kind of dissect itself into nowadays business analyst, right? The people who can understand, let me minimize this so you can see better, who can understand in the analytics continuum, the business understanding, what it is that we should be solving for the business to add value to the bottom line, right? And then on the data understanding, we have data analysts, data wranglers. Some people call the subspecialty as data whisperers. They can actually talk to data and make data talk back to them. That's data science, we need to dissect. And we have data engineers that convert data into a format that could be easily and readily used for different data science, business analytics tools. And data scientist with this refined, scoped down definition fits perfectly into model building, model testing, insight creation. The fifth step in the continuum, for those of you who have taken analytics courses, you know what I'm talking about, CRISP, DM, standard process. You check to see whether or not your findings meet and exceed the expectations of your business understanding, your business problem. If so, you deploy. And every step in the business process requires different skills that are kind of encapsulated under different personas, different titles, job titles in analytics continuum. So the short story is that the data scientists are now dissect into data wranglers, data engineers, machine learning engineers, business analysts, BI analysts, and data scientists. And of course, the analytics project manager kind of oversees the whole process from start to end. You can also link those new titles to each of the three echelons that we use to characterize business analytics data science into different layers. So descriptive is more like BI or data analyst. In the predictive side, more often than not, the title that we often see is the data scientist, which actually works very closely with the data wranglers and data engineers. And the prescriptive is still the same title as it was 60 years ago. It's the OR, operational research analysts that can take what the descriptive and predictive produced as output and find the best, most optimal solution to a given problem. So why try KNIME? Why use KNIME for teaching, for learning, for even practicing, at a commercial as a consultant in the real world? Number one, well, I try to use this top 10 list analogy from David Letterman, for those of you who know, right? So number 10 is ease of use. It's extremely easy to use, very intuitive, very visual, very logical, right? If you were to come up with your own tool, very logical, this would be it. It's very easy to deploy because it actually deploys to a cloud on a server platform. Usually you do that deployment in a professional setting. As a company, you're actually programming for the company. That's where you deploy your solutions. And KNIME actually provides that server extension as the commercial product. Everything that you do on your desktop, right? The model building, that's free, open source. Server components where KNIME actually makes its money to stay alive and create even better, more advanced features into the analytics platform that they actually make available to a wide audience. It's expandable. You create your own nodes, but you can also consume functions and capabilities in R, in Python, in H2O, and a lot of the other seemingly competitive platforms. KNIME plays nice with everyone. There's a huge community because it's open source. Thousands of people in the forum and in the hub answers questions. If you have a question, if you go to forum, there's a really good chance that you're going to get an answer shorter than you would expect. Scott here is one of those very active KNIME data scientists who's very active on that forum to answer questions. Whenever I go there, I see more often than anyone else. But you might get answers, solutions, not just a short answer, but even a worked out workflow might be provided to you to solve your problem from the community as well. You might actually get those answers. Connectivity, rich functionality. Some of the, again, before KNIME, I was using a tool, used to be called Clementine, then it called SPSS Modeler, then IBM bought it and called IBM Model. So within that, you have very similar pipeline workflow type model building constructs. But if you dig in there, you'll find like 20, 30, 40 nodes that does everything. KNIME with initial install comes over 2,000 nodes. Now you might say 2,000 nodes, I cannot learn that in a very short time, but turns out ones that you actually need to use, maybe less than 30. I might be using up to 50, but believe me, not any more than that. Unless you get into something very specialized, like time series forecasting, there might be another 100, 150 nodes. If you want to get into text mining, there might be another class library that you can download, install, and enhance the capabilities of the platform. So platform is very rich in functionality. That richness also reflects very low level representation of what analytics actually stands for. So if you have taken my course, I'm all about data, very low level data pre-processing, taking the raw data, turning into analytics ready format. And I don't want you to do it in Excel because there's a really good chance you're going to mess it up. If you do it in KNIME, because it actually maintains the integrity of the data, both on the rows and columns, everything that you do will be a separate function represented with a separate graphic icon called node. It's open source, it's platform agnostic. So I used to have tools that required you to, if you're using anything other than Windows operating system, you have to have a virtual machine in your computer to be able to run it. Now, quite a few tools, KNIME, leading the pack, runs natively on Windows operating system, Mac operating system, as well as Linux operating system, which makes it very easy for the instructor to actually manage. And it's open source. I mean, everything is open. You can go in there and change it and create your own modules. You can do that. It used to be Java-based. If you want to create your own nodes, your own functionality. Now the latest version actually accommodate 100% in Python. You can write your own function, which embeds directly into KNIME, and you can drag and drop it. You can share it with the community. Maybe KNIME likes it. Maybe future versions of the KNIME might actually include that node as one of the default nodes that comes with the initial install. Number one, it's free. And it's not just like free, it's completely free. You can use it for education, meaning that you can learn with it, you can teach with it, you can take it to the real world and do consultancy and make money with it. So it's free for everything. You don't have to actually fill out forms or waivers. And it's not the scaled down version. A lot of the commercial tools might actually come free, but they kind of limit the memory usage, limit the number of processors that you can actually use. So again, KNIME comes with everything. And that's why it makes an exceptional tool for educators in every college, every department, but especially because I'm in business school, especially for business school, for business students, because it's all visual, all intuitive. And by doing so, right, because it's visual, it's kind of Lego, putting them together to create the big picture. right? I can focus on the best practices, what data science is, what analytics is. I can focus on the problem, the process of generating the solution, and then interpreting solution and tying it back to the business problem without losing track of our thoughts, of our attention at the details of a programming language, where you put a comma or semicolon, or what is the sequence in which the parameters should, I mean, there is nothing wrong with that. If you're gonna be a data scientist, you're gonna know Python. But one tool is not enough. You're gonna need a toolbox. You're gonna need visual tools, you're gonna need programming tools, you're gonna need a lot of savvy experience in confidence in using SQL, using NoSQL. You know, how do you access their Perl, maybe scraping websites, because data is the raw material. You need to get it in the form that it presents itself to you, and then go through this data engineering to turn it into analytics ready format. Well, it's so easy to get started. Just go to KNIME.com or KNIME.org, download it. The visual interface is very intuitive. I remember first time I kind of looked at it, I'm like, you know, it's just so logical the way it's organized, kind of laid out the whole screen where you actually get your notes and glue them together. And every edition of the software make things even more intuitive and easy to do. So wait for the next actually version that's going to come out very soon, which is going to be significantly different than the version that we're actually using. All right, I'm not going to go through this details, because if I have made my point, quite likely you're going to go and check it out, and you're going to learn all of these in a very short time. So the left-hand side, the KNIME Analytics Platform, that's free desktop tool that you install and use to build your models. And then if you're an organization who wants to use those models for decision-making, for decision analysis, for business process, then you use the server version of KNIME, so you can manage the models, the versioning of the models, linking the models to whatever business process. They actually help make smarter, better, faster decisions. Okay? And when you're in need of a starter, maybe you need a workflow that's already built. Oh, KNIME comes with a lot of examples, but let's say that's a unique example. If you go to Hub, there's a really good chance that you might find quite a few of those examples, workflow data packaged together that you can reuse, you can download and reuse. The way in which that actually works is kind of almost unbelievable. You drag the workflow from the web page onto the KNIME user interface, right? Download, go in there, import, you don't have to do any of those. So all the shortcuts are available in KNIME Analytics Platform that you can actually use to get the notes, the data in. Infomercial, if you're gonna teach KNIME with your analytics data science courses, check out our textbooks, because we kind of, with every new edition, working more and more of KNIME into our show and tell in the textbooks. The new book that's gonna come out in a couple of months, on the left-hand side, we have a chapter, almost 100 pages long chapter called Analytics Tool Landscape. So it reviews pretty much any and every tool, almost fully comprehensive in the market. What are the pros and cons, how they do what they do. So you would have a very objective view of which tool fits to your needs, your wants, either as an educator or as a professional who actually develop solutions. So I'm going to stop here and then turn it over to my colleague to get his presentation going. He's going to be talking about how to use KNIME with educational data repositories to identify at-risk students in college settings. Okay? And he actually used deep learning. We actually collaborate on that. And explainable AI. So it will be a lot more interesting, and he will probably be more workflow driven than like me boring, you know, slide after slide. So Behrooz, can you hear me?
Yes, thanks, Dr. Delen. Hi everyone. My name is Behrooz Davazdahemami. I'm an assistant professor of IT and data analytics at the University of Whitewater, University of Wisconsin-Whitewater. Also a former PhD student at Oklahoma State. So Dr. Delen was my advisor actually, and the first time I heard about KNIME from him. So since 2017. I've been using KNIME for pretty much all my research projects. I did my PhD dissertation mostly using KNIME, so pretty incredible platform, and you'll see some a quick demonstration of that in my presentation. So let me just quickly share my screen with you. Okay, the topic we're going to talk about is how to use and explainable machine learning for mitigating the student attrition. So just a quick note about the context. You know that the main funding source of the academic institutions is the tuitions. But for a long time, for decades actually, their main concern, their main challenge is how to retain their students, because what happens in reality is that usually in a 6-year window, only around 60 to 70% of the students stay at the institution, but around 30 to 40% drop out. So since the emergence of the data analytics methods, there has been a lot of studies with the aim of first of all predicting the students at risk, and also there has been some research to find the main risk factors leading those students to drop out. But one issue with those research works is that they usually use high-level interpretation approaches. So they try to provide insights that is like one-size-fits-all type of treatment for that issue. So factors like GPA of the student, like the number of past credit hours, those are identified as the risk factors. But we still see that students that have very good GPA, or they have successfully passed all their credit hours, but they still are very likely to drop out. So our goal in this research was to use some switch here to use some local explainable approach to better explain the reasons for actually the risk factors for each student. In terms of the data set, we use a pretty large data set containing various factors. Let me just open the data. So it has more than 38,000 records, all from freshman students. So in their first semester at the Oklahoma State University, and it contains more than 45, specifically 49 features. So it contains features on the demographics, on the pre-college statistics, on the educational factors at the college, also college financial, whether they got any loans or something like that, and also the socioeconomic factors. A pretty large data set, but this data is pretty clean. So I have done some pre-processing on that. So for example, here I've used the string manipulation. It's the kind of text mining type of node in KNIME, and I've used that here to extract the student IDs from the row ID column. So the first 6 characters of the row ID is extracted, and a new column for that called the student ID is created. So that's just some example of the type of things they can do with text. Also, I excluded some of the variables that were not relevant to prediction. But here in one-to-many node, because the approach we're going to use for prediction was deep neural network approach, and the neural networks basically only accept numerical inputs. And because the original dataset contained so many categorical variables, so this one-to-many node here converts all the categorical variables to multiple binary variables. So for each level, for each possible label in those categorical variables, a binary or 0-1 variable will be created. So before this one-to-many, you can see that we had only 46 columns, but now that we expanded those categorical features, we have 267 features in the data. Going forward, we did partitioning using this partitioning node here. So 80% of data was kept for training the model, and we did stratified sampling by keeping the same proportion of zeros and ones from the positive and negative class. The data was pretty unbalanced. So around 80% of the cases was positive cases. Those students that actually dropped out in the next fall, and sorry, 80% was negative cases and 20% was positive cases. So I will show you what we did to handle that imbalance. So for both the training and testing data, we normalized the variables to actually bring them into the same scaling level to prevent any bias. So this normalizer nodes here just normalize all the numeric variables to the using a min-max normalization into the range of 0 to 1. So everything is in the same range. With regard to the deep learning, so first of all, KNIME, I think, is one of the few platforms, actually low-code platforms that supports 3 different libraries for deep learning. So there's Keras, there is DL4J, and also TensorFlow, probably the top 3 popular platforms and libraries for deep learning. So for this project, we used Keras for doing the prediction model and using deep learning for that. I'm going to start with this network architecture, which is the first requirement for doing deep learning. So I'm going to open this meta node. So first of all, for using Keras in Python, it is not one of the actually the set of nodes that is installed by default. So you need to add the Keras integration, and if you Google that, there's a step-by-step instruction on the internet, on the KNIME website, to add the Keras integration and the set of Keras nodes to your KNIME installation. Also, you will need Python, a version of Python installed on your computer. So, but my recommendation specifically is to use the Anaconda distribution of Python because of its better package management. So that's all. And then in that step-by-step instruction, you will be instructed how to create a Python environment that is compatible with Keras, and whether you want to use CPU or GPU for deep learning. All of those options are available to you. Anyways, for creating a network architecture, every deep network in Python, in KNIME, starts with an input layer. So from the nodes, you find the Keras input layer. For this problem, our data set is actually one-dimensional array. So all we need to do is to set the number of predictors that we have in the data set. In this case, is 265 here. If you are analyzing, for example, image data set, then the input layer would be two-dimensional. If there are colored images, they are three-dimensional. So you set up the dimensions of your input layer here. For this network, we have used the, used our dense layer, and there is a context dropout layer here. Dropout layer is a common approach that we use for. Can you hear me?
Yes, we can hear you.
Okay, sorry. I think my connection out. So the dropout layer is basically used for slowing down the training process in a neural network. Especially with small data sets, the neural networks are very likely to get overfit very fast. So use dropout layer, and this dropout layer actually randomly ignores some of the neurons in each iteration. So in each passing of the data through the network, I've set here that 20% of the nodes, 20% of the data inputs are being ignored. So it helps the network to train slowly and to prevent the network from overfitting very fast. Also, the Keras dense for the output layer, because it's binary classification problem, we set the activation function to sigmoid, and there's only one unit or one neuron at the output layer. So we set up that network architecture. Then we get to this Keras network learner, in which the training process happens. So it needs at least two inputs. One is the network architecture that we created. The second mandatory input is the training data. Optionally, we can connect the validation data to the third port of this node. So let me open up this node settings. So there are several tabs in there. For the input data tab, you need to specify your predictor variables on this green frame. You move all the predictor variables there, and they should be a match between the number of predictors and the shape of the array that you set up in that input layer. So the shape was 265, and there are exactly 165 variables here. In the target tab data, for example, we have this target variable. So it's a binary variable with 0s and 1s, showing attrition or dropping out of that particular student if it is 1, and retention if it's 0. One interesting feature in KNIME for doing deep learning using Keras is this custom loss function. So KNIME offers a group of standard loss functions that we can use for different purposes. So for binary classification, usually binary cross entropy is the common loss function. But the problem is that that loss function assumes that we have a balanced data set, or the proportion of zeros and ones is pretty much the same. So it assigns the same penalty to the false negative and false positive predictions. But if we have an imbalanced data set, like what we have here in this project, we can customize those loss functions. So we can activate this radio button for custom loss function and some Python coding here. We can see that, for example, I have assigned different weights to false positive and false negatives. So 86% weight for each false negative, 14% for each false positive. So by doing that, we are kind of making up the imbalance in the data. So for each positive case that is incorrectly predicted, we assign more penalty, and we kind of tell the model that we want those positive instances to be more accurately predicted. So that's one interesting feature. Here also there are many hyperparameters that we should set up when training the network. In practice, it takes a lot of time for us to come up with the best combination here for the hyperparameters. In the original project that we did, we used some a genetic algorithm to come up with the best combination. But here I just went with the default just for demonstration. So most of those numbers are what you see as default. Also, you can choose the type of optimizer for optimizing the network weights. So I used the Atom here. I'm not going to run this node again because it takes a lot of time to complete, but I'm going to show you this very good feature called Learning Monitor. So we open that. You can see two charts here in the two tabs for accuracy and loss. And those charts actually are being created in real time when you start training the network. So my network is already trained. So at the same time that your network is being trained, you can, in real time monitor the accuracy of the training data as well as the validation data. You can monitor the gap between the accuracy and loss function. And as soon as the gap starts to increase, you can stop the learning process using this button down here. So you don't have to be worried about overfitting. You can easily interrupt the process of learning in the middle whenever you feel that the model is getting overfit. So once the model is trained, we pass it to a keras computer, which uses that model weights to predict the probabilities for the test data. So for each instance in the test data, it will give us some probability here in the last column. And that probability is the probability of belonging to the class number 1, which is corresponding to attrition for each student. So in the next step, a rule engine node is used to convert those probabilities to some labels. So anything above 50% is considered as 1. Anything below 50% is considered 0. So we have some labels, and then we match those labels against the actual labels that we have for the data and use the scorer node to calculate the accuracy and other performance statistics of the model. So in this case, the overall accuracy of the model was 82%, and the sensitivity or recall for the positive class was around 76%. Not bad, but if you spend some more time on optimizing the network hyperparameters, you probably can get better results. Also, the ROC curve Pretty good, around 8.88 is the area under the curve. So we know that it ranges between 0.5 and 1, and the values closer to 1 show that the model is performing better. All right, so up to this point, we have a prediction model, and it's a completely black box prediction model. I mean, the predictions are pretty reliable, but we have no idea what are the risk factors. So our work actually starts from here. So in these last two steps, we are going to use the SHAP method, the SHAP analysis method, to actually calculate some importance scores for each of the features. So let me switch back to my slides. Very quickly go through the logic behind the SHAP analysis, and then we'll go through that workflow to see how it works with KNIME. The SHAP, which stands for Shapley Additive Explanations, actually has roots in the game theory, and specifically in the Shapley values of the game theory. So if you consider the outcome of the model, which in this case is the predicted probabilities for each observation as the gain, then the predictor features that constitute that probability can be considered as the place. The SHAP values that we calculate are actually supposed to represent the contribution that
Oops. That's what happens. Sounds good. Yeah, it looks like Behrooz had a internet connection problem.
Yeah, it looks
So let me continue where he left off. We've been working on this project for quite a long time, more than 10 years, published several papers on it. The difference about the study that he was presenting is that it's using deep learning and it's using explainable AI. Now, let's say we collected a whole bunch of data from OSU freshman student records, right? You may or may not know, but we probably have around 15 to 20% attrition rate at the freshman level. So students, 1 out of 5, roughly, who signs up, register for the first semester, they drop out at the end of the first year. So they don't show up for second year. It's a big rate, percentage. We want to reduce that. The only way that we can do that if we were to know who are those students who are not likely to show up, because we have 5,000 freshman students, we cannot chase every single one of them, right? So we need to know who are more likely and can we actually do something about it. So not only knowing what factors kind of leads to attrition at the freshman level, but also at the individual student level, what could be done. So that's what SHAP in line, this explainable AI techniques brought to bear, is that it not only tells us in general which factors are more important. Is it residency? Is it the high school GPA? Is it the the age of the student or the residential status of the student, whether or not he or she lives on campus or off campus. But it takes into account individual student and then provides individualized intervention information. That's a game changer, right? So in the sense that not only we know the let's say top couple of hundred students who are at risk, but at the individual level, we would know what might impact their returning back to school in the second year. Yeah, so that's where the explainable AI and deep learning kind of comes in the picture. Yes. That's a good question. That is a good question. But these, so the question had to do with whether or not the SHAP values. Okay, Behrooz is back. We'll let him answer. How about that?
Hello. Sorry.
Can you hear me?
Yeah.
So while
Sorry
you were offline, I
yeah.
was talking about how SHAP provides us at the individual level explanation so that we can craft customized intervention. So one of the questions from the audience is that in the SHAP values, is there any interaction or are they individualized as they actually described in the model output, in the explanation?
Okay, I am going to go through the details in my slides, so just give me a minute. Here's a very small but useful example to learn how SHAP works. So let's say that we have three predictor variables, age, gender, and job, and the goal is to predict the income of a person, the income. This diagram, which we call a power set of features, it shows all the possible coalitions of these three predictors. So if we consider none of them, that is one possibility. We can consider each of them separately. So for three predictors, we will have 2 raised to the power of 3 or 8 possible coalitions. So what the SHAP analysis do is that it performs the prediction using the predictors in each of these coalitions. So for example, let's say that for a particular person, using none of the predictors, the prediction of the income for that person is $50,000, which is basically the average of the income across the whole sample. Only using age for predicting income for that person, we come up with 40,000. Only using gender, it's 48,000. So each node in this diagram actually shows one of the coalitions, and each edge shows the inclusion of a predictor variable which was not part of a coalition in the previous step. Okay, so let's consider age specifically. So considering age, then all these highlighted nodes will be the edges representing the inclusion of age in a coalition, which it was not part of in the previous step. So for example, here for the first one at the top, it says that if going from no predictors to only having age as a predictor, the prediction for income goes down from 50K to 40K. In other words, we can say that the marginal contribution of age is negative $10,000. But same idea for other edges containing age. as the incoming, as the new predictor, we can calculate the those marginal contributions. Also, each of these edges have a weight. So that weight is simply the inverse of the number of edges that we have at each step of this tree. So for example, for this one, for W1, for going from level 0 to level 1, we have 3 edges. So the weight for W1 would be 1/3. So using those marginal contributions and those weights, we can calculate a weighted average for that particular feature and that particular instance. So in this case, the average marginal contribution of H is negative 11.33, and that is considered as the SHAP score for that feature for that particular person. It is not the same as regression coefficient. It doesn't mean that with each additional unit of age, the income goes down. This is a value particular to this person and to this feature. For another person, we might have a positive contribution for age, depending on the combination of the features, combination of the feature values that we have for that person. We might have a different value. So these scores are both feature specific and instance specific, and very personalized scores. So very different from the high level, group level type of feature importance scores that we see. So let me go back to the loop. So one big challenge with using SHAP for analysis is that, first of all, if you want to go through all the instances in the test data sample, it'll take a lot of time, because for each of those samples, we have to go through all the possible collisions, calculate the marginal contributions for all of them. So to decrease the number of samples, we usually use K-means clustering. So let me open up this component node. So here we have used the K-means clustering to cluster the 7,000-8,000 instances that we had in the test data set into 100 clusters. And then we randomly select a representative from each cluster, assuming that all the items in that cluster are similar. So instead of going through 7,000 or 8,000 instances, we only use the 100 representatives. Another challenge is the number of possible collisions, which exponentially grows with the number of predictors that we have. So with 3 predictors, we saw that there are 8 possible combinations, but imagine when we have 265 predictors, it means that we will have 2 raised to the power of 265 possible collisions of the features. So obviously it takes forever. If you want to go through all those collisions and calculate the marginal contribution for all of them. So what we do is to request a SHAP algorithm to just randomly choose the subset of those collisions in each run and only calculate the marginal contribution for them. So here we have 2 actually nested loops. The outer loop is signified by these 2 nodes, chunk loop start and loop end. Actually, they are making sure that we go through all the 100 instances that we have. So each instance is passing through the workflow once. This inner node, this inner loop, which begins with the SHAP loop start and ends with the SHAP loop end node. Let me open up this SHAP loop start node here. So this SHAP loop start basically is responsible for forming the subset of the collisions. So in this example, we set 1,000 as the number of collisions to be checked for each instance. So it forms all those collisions. It passes the data to this predictor node, which gets the network information from the train network up here. This SHAP loop end, on the other hand, actually calculates the marginal contributions. It calculates the weighted averages and basically the SHAP scores. And we do that for all the instances. So at the end, we have the SHAP scores calculated for every single attribute and every single individual in the data set. So now we have those SHAP scores. So this last part of the workflow is responsible for actually explaining the, zoom out a little bit, for explaining and interpreting the result. So here, using this variable creator, we can choose one of those 100 students to show the interpretation for them. So let me set, for example, this number to 66. Okay, so there are two branches here. So very quickly, the top branch is responsible for extracting the SHAP score from the list of all SHAP scores that we have in this loop end node. So we're using the student's the student ID. We extracted SHAP node. Here we have a Python script node. So Dr. Delen talked about the integrability of KNIME to different platforms. So here we have used the Python, small Python code that run up to this point. Small Python code to kind of reverse the one-hot encoding process. So we put together all the levels, we add up the SHAP score for all the levels of the categorical features, and calculate a single score for each categorical feature instead of having multiple ones. In this below branch, we actually use the original data set. So it's a copy of the original data set. We extract the original values of each feature. So we put together the original values, the SHAP scores, using value lookup node. So by matching the students' IDs, and at the end we use this bar chart. So let me just open the result. So for a student number 66, for example, here's the list of the most important factors. First of all, we can see that the predicted probability of attrition for this student is pretty high. It's 94%. And it shows that for this particular student, the most important factors, the top two factors, are the total pass rates, the ratio of passing credit hours is only 50%. So and the student has failed in 50% of the courses. Also, the GPA for the fall semester is categorized in the low category. So it looks like that for this particular student, the biggest issue is the biggest challenge is that he or she needs some, educational assistance. Okay, let me switch to another student. Okay. If we choose, for example, a student number 87. And create a chart again. You can see that the important features is pretty different here. First of all, it's 50% likely. So still we consider this student as a risky student, but we can see that even though this student has a low GPA, but GPA is not at the top of the list for the risk factors. So for this student, it looks like that other factors are more important than GPA. So specifically, for example, assigning no fall semester loan to this student is a factor. So it looks like that for this student, maybe the best type of intervention would be to offer some financial aid instead of or on top of the educational assistance to help and to actually prevent that student from dropout. Okay, I'm gonna stop here. Sorry if I exceeded my time, but there are a lot of details that if you have any questions, you can go through them. Otherwise, I would be happy to share the workflow with you to look at it later.
All right. Any question from the audience here? I know it was too much of information in a very short time, but in the big picture sense, right? Idea is to use this later machine learning techniques like deep learning and explainable AI to provide actionable insight at an individual level. This is brand new. We have never had this. So we used to use this generalized information as to which factors are more important in predicting the outcome, right? There are a few papers that we published and it was all about that. So the way that it used to work is that we used to follow this leave one out methodology. So we built the model using all of the variables. Then we take one at a time out and see how much prediction suffers in the absence of that variable. So more that it suffers, more important the variable is to the prediction of the system, right? It's like, letting one of your players sit on the bench while you're playing. So whichever the player that sits on the bench and you get scored the largest margin is probably the one of the most contributing player in your team. So that's how the variable importance sort of work in machine learning, because it's not like regression where we have explicit beta coefficients that tells us the story. Okay.
The question online from Brian: what was the biggest surprise during this process?
Behrooz, can you hear it?
Not really.
Yeah, the question has to do with what was the biggest surprise, things that was not expected in this project?
Probably the biggest surprise was the inconsistency that we had between the high level interpretation measures and what we get in SHAP for each individual. So using high level interpretation approaches like the ones that Dr. Delen just explained, we usually get some fixed number of factors at the top, at high risk factors like the GPA of the student, like the financial aid. But when we run the SHAP analysis for each individual student, we realize that applying those same type of intervention to all students might not be very effective. In case that actually, in fact, there are some students that are in very good condition, both from an educational perspective, also don't have financial needs, but they have some other needs. For example, their main risk factors might come out as their residential status, whether they are living at their dorm, or whether they are active in their Greek life at the university. So the type of intervention can be personalized using those insights. We are not going to prescribe the same treatment for all the patients. If you look at that as a medical problem, but we come up with a personalized type of intervention, and our results showed that there is a lot of inconsistency between the top risk factors when you look at the group as a whole, and when you look at each student, each instance in the data set. So that kind of confirmed the importance of this study. Shows that it's better to go at the personal level for doing and designing the interventions.
Thank you, Behrooz.
Other questions?
Here's another question.
There is, okay.
How many more factors or columns in the input table could be handled in this model?
Behrooz, the question has to do with how many more inputs in the model can be handled, because you talk about the dimensionality as we increase the number of variables included in the model, the computational burden, right? Expense is increasing exponentially. So how many variables have you used, and how many more could have been maybe reasonably handled in the model?
Basically, we use all the variables, but the thing is that instead of going through all the possible coalitions of them, so let me open up this SHAP loop start node. So here you can see that all the 265 variables that we had are included here. But here in this sampling option setting, we tell KNIME that instead of going through all the 2 raised to the power of 265 coalitions, for each instance, just randomly select 1,000 of the coalitions. If we have more time to run the workflow, we can increase that. But I think anything between 1 to 5,000 is sufficient. So instead of going through all the coalitions, we use only 1,000 of them for each instance. Also here in the SHAP loop end, we use this regularization explanation option, which tells KNIME that only consider the top 50 factors in each iteration for each instance. So out of the 265 features for each instance, only the top 50, for the top 50 we calculate the SHAP scores, and for the rest we assume that their contribution is so trivial that we can set them to 0. So using those tricks, we kind of decrease the computational power requirements and also time requirements for the SHAP analysis. But technically, there is no limitation on the number of, if you have enough, computational power, you can go through all the coalitions, you can calculate the SHAP score for all the features for each instance. The larger those numbers, the more reliable the results. But usually going with the top 1,000 coalitions or the top 50 features for having 200 features, and we can still get some reliable results, and the results are makes sense usually. Okay.
Thank you, Behrooz. As he said, there really is not a limit as to how many variables that you can handle in deep learning, because deep learning kind of connected to or motivated by the big data. In big data, the number of features, especially in images, in text, will be tremendously large, much larger than 250 some odd variables that are used in this model. So it all depends upon how much horsepower you have in your machine. If you're using cloud analytics, cloud-based, server-based systems that are boosted with a lot of GPU power in addition to your CPUs, then the kind of dimensional that you can handle probably be sort of unlimited, only limited to your capabilities and how much you're willing to pay for it.
Just another important point is that we can choose which variables to include here. So maybe not all those variables are important to us to use for interpretation. Okay, so we can, for example, exclude the gender or age because we can do nothing about them in the intervention. We cannot change the gender of a person or age of a person. So we just include those variables that we have some control on. We can do some intervention to change them, and that also helps to decrease the computational requirement and also the time requirement for the analysis.
Thank you. Is there any other questions, Scott?
Any other questions from online? Do we have any others from here?
Is there any question from the audience here? All right.
I have one.
Yes.
So you're a data scientist, you built your model, right? You can explain your predictions, by sampling, SHAP. But what is the next step to actually making this useful for an admissions department, right? Where do you go from here?
Excellent. Did you hear that, Behrooz? So what would be
No.
the next step now that you have the model built, you have good predictions, you can do explanations in the generalized as well as individualized level. So how does a university use what you have just built?
Yeah, very good question. Actually, that's the main purpose of this study, to come up with some personalized intervention. So it depends on the individual we are analyzing. So let me just open up this bar chart for this person, for example. So it's a different story for each person. We cannot, come up with a prescription for everyone. For this person, for instance, like we can see that, for example, this person, even though he or she has a low GPA, but the SHAP scores say that its contribution is almost zero to the chances, to increasing the chances of dropout, probably because the total pass ratio for this person is 100%. So the student has passed all the courses, but with a low GPA. So it tells that maybe we should look for other factors instead of offering some educational help, some tutoring. So looking at the top factors, top risk factors, we can see that, for example, the fall loan, for which the student has not received any fall loan during the fall semester, probably that is one big reason. So offering some financial aid for the spring semester could be a effective intervention for this student. Also, even though it shows that the residential life is yes, it means that the student is living at the dorm, but having no Greek life is identified as the third risk factor for this student. So maybe encouraging the student to be more active in the extracurricular activities, in the Greek life activities, can help the student to get adapted to the college environment better, to encourage the student to stay there for some more semesters and ultimately to return the student. So it's a different story for each student. And the ultimate message of our research was to analyze these stories for each person instead of just trying to apply the same intervention to everyone, which might not be effective.
Yes, thank you, Behrooz. Just to add, that's the individual level intervention. So in addition to what to do with the individual student, how would this whole system, right, prediction system can be used or utilized by Student Success Center, the admission, VP of admission in a university setting. So you can actually run the model, right, periodically, and then based on the data, you identify at-risk students, and then depending upon how much resource that you have on hand, you can say, maybe I can deal with 200 students, and then those at-risk students at 200, top of the prediction for individual level, you can figure out what might work for individual students to increase the chances of persistence, so they can actually show up for second year. As far as the reusability, of course, you would probably have a server deployment of it plugged into your admission office database, and then periodically run to identify at-risk students, create the intervention plans accordingly, and then go about in retaining more students, increasing your retention rate.
That's what I was thinking about. Somebody, an admissions officer who's never seen KNIME, would not know anything.
Oh, yeah,
about KNIME,
they
right?
should.
How are they going to give it?
Exactly. So their database is going to be leveraging models sitting in a server, or maybe on a local computer, running it against the current freshman cohort, identifying at-risk students, for each student coming up with what factors need to be improved to increase the chances of retention, right? For students to show up for second year. Excellent question. Any other question? And we don't have anything online either? Okay, so it's about the time to wrap it up.
Okay.
Scott?
I'll come do that. Thanks everybody again for showing up for the Data Connect. We have these events periodically throughout the year, usually a few times a month. Some of them will be, not in the US, some of them are in Europe, some of them are in other countries, but most of them are online, so you can always tune in and see what folks are doing with KNIME software, how they're actively using it, and the benefits they're getting from it. If you have any questions or follow-up, I would suggest to you, you can visit the KNIME forum. Dursun already described that before. We have threads dedicated to the different events we do, so you can come post your questions there, and it's also just a good resource for learning and putting into practice the stuff you might be doing with KNIME. Also, the KNIME Community Hub, hub.knime.com, where you can check out a lot of these workflows. In fact, maybe I'll ask our presenters if they can post maybe an example workflow of what they've shown today on the Community Hub, so that you could download and try it out yourself. Maybe a little bit trickier than some others to set up, because it does involve that Keras extension and some Python stuff on the back end, but we can get you squared away with that. So thanks again for attending. Hope you learned something. I did, and hope to see you at the next KNIME Data Connect event. Thank you.